Science leads to a system of laws and theories, so unsurprisingly, we're going to need to lay down some laws of chemistry. The first person to go down this road is Antoine Lavoisier. He's a famous French chemist. He's actually considered the founder of modern chemistry. Before chemistry, you have alchemy, where people are trying to do things like turn lead into gold, essentially through hocus pocus. But Antoine Lavoisier applies the scientific method. And so that launches a whole new realm of chemical discovery. So the first thing, he does some experiments. He oxidizes some metal to produce rust. He's also able to combust oxygen and hydrogen to produce water. And he can do the reverse. He can decompose water into hydrogen and oxygen. And what's really important is that he writes all this down, and he's very good in his methodology. And because of that, he discovers the first law of chemistry, the law of conservation of mass. So whenever he does his experiments, he observes that the total mass in the chemical reaction remains constant. This is actually fairly surprising. It might not seem that way because we may be comfortable with this sort of idea, but if you think about it, lots of properties are not conserved. Volume certainly is not conserved. If you produce foams and gases over the course of a reaction, something like color is not conserved. It can be destroyed and generated. And there's no particular reason to think that mass should be conserved throughout a reaction. It might very well seem that it's not. If you have gases formed and they seem to float away, suddenly your sample weighs less. But when Lavoisier takes some tin and he rusts it in a sealed container and he measures it before and after, the mass does not change. And he confirms that this is true for his other experiments as well. As an example, let's say that we have a car engine and we supply it with 20 kilograms of fuel, and we allow this to completely combust with atmospheric oxygen. So we run the tank down to empty, but we capture all the gases from the exhaust, and we find that it produces 57 kilograms of exhaust. So how much oxygen did our car consume over the course of the drive? Well, according to our law of conservation of mass, the total mass does not change. So whatever the initial mass of the fuel and the oxygen that reacted with it were, that's also going to be equal to the total mass from the exhaust, assuming we use up all of our fuel. So now all we have to do is just solve for our missing quantity of oxygen and plug in. So the mass of oxygen is going to be equal to the mass of exhaust minus the mass of fuel, which is 57 kilograms minus 20 kilograms. That must mean that 37 kilograms of atmospheric oxygen were consumed over the course of this reaction. Another pioneer and contemporary of Lavoisier is Joseph Proust, and he's also doing some similar experiments. And in so doing, by also taking good measurements, he notices a pattern. He discovers the law of definite proportions, also called the law of constant composition. What this states is that all samples of a specific compound have the same elemental composition by mass. So if one sample of a substance is 10% copper, then another sample of a substance will also be 10% copper. And importantly, this does not depend on the source. So if I get my copper oxide from a mine in Nigeria, it's going to have the same composition by mass as copper oxide that I produce in a laboratory or that I get from a mine somewhere else. Now again, this is also a controversial conclusion. In fact, many people today would dispute this assertion. For example, people who believe in homeopathy would say that it matters immensely if you have a water sample that came from such and such conditions versus such and such other conditions. Now, in chemistry, we have not found any evidence of that. So we are going to stick with the law of definite proportions, which says that compounds are always going to be the same, and it doesn't matter whether they were produced in the lab or grown organically. As long as they're pure samples, then they're identical substances. Example which shows how this is useful. Let's say that we have a 22 gram of copper carbonate. This is actually something that Proust was working with. This is how he originally determined the law of constant composition. He's also working with some metal oxides. And so we have a 22 gram sample of copper carbonate, and it's produced from 11.3 grams of copper. So how much copper are we going to need if we want to scale this up to 140 grams of copper carbonate? We can apply our law of definite proportions or constant composition. So that's going to state that the ratio of these masses, their percentages, remains fixed. So whatever quantity of copper belongs to sample 1, if we write that as a fraction or a percentage, that's going to have to match up with our second sample, which we haven't finished generating yet. We can plug in values and cross multiply. I'll plug in our 11.3 for our known sample and 22 grams for that sample. 140 grams is the total mass of our unknown sample. And we'll leave the unknown quantity for the copper as an x. Now we solve for x, and it comes out to 71.9 grams of copper. And if you inspect this, you can see that it's approximately a 2-to-1 ratio. So to produce 22 grams, we need 11 grams, which is about half of it. And again here, to produce 140 grams of the copper carbonate, we need about 70 grams of copper, which is about half. So that's what this law of definite proportions is saying. That if half the mass comes from one substance in one case, then that's going to be true in all other cases. And that lets us write down some equations to express it. Our third and final fundamental law of chemistry comes in 1804 due to John Dalton. And this is the law of multiple proportions. It states that when chemical compounds combine, they do so in the ratio of small whole numbers. Now let me just show you an example of that in action. I think that will make it more clear than trying to explain the terminology up front. So let's do an example where we have two chemical compounds. One we'll call carbonic acid, one we will call carbonic oxide. And we've done some experiments to find out their elemental composition. We can separate these into oxygen and carbon. Now we want to demonstrate this law of multiple proportions. That there's this ratio of small whole numbers guiding the creation of these substances. All right, so the first thing we're going to do, we're going to produce one of these substances. Let's choose carbonic acid. And we're going to do this using 1 gram of carbon. So we take our 1 gram of carbon and we combust it with oxygen in the atmosphere as much as it needs. And we get 3.66 grams of carbonic acid. So how much oxygen did we use? Well, if you recall the law of conservation of mass, that must mean that we used 2.66 grams of oxygen, because 2.66 plus 1 equals 3.66. So we started out with 3.66 grams total, and we wound up with 3.66 grams. That's the law of conservation of mass. Well, now we want to do the same thing for the carbonic oxide. So we'll produce our carbonic oxide using 1 gram of carbon, just like before. And this time, when we react it in the open atmosphere, it only requires 2.33 grams, or it only produces 2.33 grams of carbon oxide, which means that we only consumed 1.33 grams of oxygen. Now this is where we actually apply this law. We're going to compare the masses of the oxygen used to make the carbonic oxide and to make the carbonic acid. And when we do that, we could compare them by constructing a ratio. Comes out to about 2.0, which is a 2-to-1 ratio. And that's a ratio of small whole numbers. So we have verified that the law of multiple proportions applies in this case. And we form these two different compounds. The substance which combines to form them makes up a ratio of small whole numbers when we compare their masses. Well, that law of multiple proportions is kind of odd, right? It's not very intuitive why it exists or where it comes from, but it's very surprising that when we take entirely different substances, we always get this curious mathematical relationship of forming those small whole number ratios. So why does that happen? Well, we'll have to speculate here. Maybe that oxygen, which we were using to produce the carbonic acid and carbonic oxide, comes in units, and so does the carbon. And so the carbonic acid had twice as many oxygen units per unit of carbon as the carbonic oxide did. So we started off with 1 gram of carbon, and we combined it with oxygen to produce this carbonic oxide. And for the carbonic acid, our fundamental unit required 2 of those, so we needed twice as much of the oxygen to go along with the same quantity of initial carbon. And so we got a 2-to-1 ratio between those masses there. Well, that's an incredible insight, and Dalton actually makes this insight, and so this led him to create his atomic theory, which states that matter is composed of elements which can be combined in complex ways, but never created or destroyed. And that's consistent with what we discovered in our classification discussion, that we could isolate pure substances into elements. If they were compounds, we could separate those into elements, but we couldn't go any further. And so Dalton says that those elements are actually fundamental building blocks, and they lead to the construction of substances in a way similar to what's depicted here.